Hello students, welcome to Vyas Edification Kota. In this series of NCERT discussion, yes, it is time to continue further with Mathematics class 12, the chapter Determinants, and now is the turn of the very interesting, very important miscellaneous exercise in which we'll have questions from all the concepts covered in the chapter. Now there will have been a lot of important things covered in this chapter of determinants. Starting from the let us say last exercise that we have covered before this, we had something called solution of system of equations using the matrix method. That was an important thing. Before that you learned how to find the adjoint and inverse of a matrix. Before that you had a few more interesting important things as well. But then those two important concepts, those two last two concepts were very important. I have mentioned that beforehand. And once again, when we are seeing the miscellaneous exercise, we will be seeing the complete chapter, questions related to the complete chapter one by one. Let's begin with the first question over here. Let's discuss this first question. What does the question say? Prove that the determinant x sin theta cos theta, then you have a minus sin theta minus x1 cos theta 1x is independent of theta. Okay. So the determinant is independent of theta. What does that imply? That simply means that the value of determinant that you find on simplifying this will not have any term of theta in it. Okay. So if you keep changing theta in this determinant, the value of determinant will remain same. That's the idea behind this. So let's find the value of this determinant in terms of theta first of all, theta and x, and let's see where does that take us. Let's see where does that take us. So you have x sin theta cos theta minus sin theta minus x1 cos theta 1x. Do you think you can create some zeros somewhere? Frankly speaking, if you would observe, there are no similar kind of terms anywhere in any row or column for that matter. You have x sin theta cos theta and so and so. And can you try to create something of that sort? Probably not. That will be also difficult, right? X minus sin theta minus x sin theta 1 cos theta, no. So let's try to evaluate the determinant directly then. The value of determinant delta can be written as delta will be equal to, okay, we can expand along the first row, x times you get minus x square minus 1. Is that okay? Minus x square minus 1 minus sin theta times minus x sin theta minus cos theta. This is what you get. That's the second term. And what else? You have cos theta minus sin theta and plus x cos theta. We have first plus cos theta first, and with that we have minus sin theta plus x cos theta. This is what you have. Is that okay? Yes. So what is that? Where does that take us? Let's take a look at this. This is equal to minus x power 3, okay, minus x. Let's multiply them together. Minus sin theta minus x sin theta will be plus x sin square theta. Minus sin theta into minus cos theta will be plus. Next, cos theta sin theta with a minus will be minus sin theta times cos theta. And plus cos theta plus this will be plus x times cos square theta. Okay. So, yes, you may have obtained some terms having theta in the value of determinant if these terms would not have cancelled. And one more thing, this would have remained as it is, this would have remained as it is, but if you see, this is also x sin square theta, this also has a term of x, you can take out that x common, yes. So this is minus x power 3 minus x plus. Can you observe that x sin square theta plus x cos square theta, you can take out x common. What you get is sin square theta plus cos square theta in the bracket. Oh, but this value is fixed, right? On changing the value of theta, this value will not change. This is always 1. Since this is always 1, this is minus x power 3 minus x plus x, which is actually equal to minus of x power 3, and that's what we wanted to prove, since this minus x power 3 is independent of theta. That's what we started with, right? That's what we wanted to prove. That's all that you have in this question. Let's discuss this next question in front of us. The question says, without expanding the determinant, prove that this is equal to this. Okay, and how are we going to prove that? Let's take a look at this expression over here. In one of the questions in the exercises which were given based on properties of determinants, exercise 4.3 or 4.4 something, you had this determinant and you were supposed to find the value of this determinant, right? Okay, and what did you do in that case? Actually, when we were solving that determinant, we reached the stage where this actually converted into this. Okay, so we have already solved this kind of a question before, yes, in some exercise. But let's repeat. In the LHS, what do we have? Now, if somebody may recall that we have a square and bc, and for finding the value of the determinant we were supposed to create some ones. Okay, and can we create some ones somewhere for subtracting purposes? No, we will not be able to create some ones directly, but then let's see. This has a BC, there's a missing A, this also has a CA, there's a missing B, this has AB, there's a missing C. Let's multiply A in this row, B in this row, and C in this row. Okay, if you multiply by something, you have to divide by something. Okay, so let's divide by A and let's multiply the first row by A. You get A square, A power 3, ABC. Okay, let's divide by B and multiply it by B in the second row. This becomes ABC. Let's divide by C and multiply by C in the third row. This is C square, C power 3, ABC. Okay, and that's the most important step that you require. After that, a simple step will ensue. What's that? Can you see that this whole column has a factor of ABC? Yes, let's take out that factor ABC common. So what you get is ABC upon ABC times A square, A power 3, 1, B square, B power 3, 1, C square, C power 3 and 1. This is what you get. Oh, these terms are similar to this. Yes, they are similar to this. Interchange. Let us say, let's bring A cube on the C3. Okay, so for interchanging, what do you get? Therefore, LHS is equal to 1 times. If you interchange any two columns, you get an extra minus sign. Okay, and what you get is A square 1 A power 3, B square 1 B power 3, C square 1 C power 3. This is what you'll be getting, right? What next? Let's interchange these two as well, and you'll get an extra minus. So it will become minus 1 square times 1 A square A power 3, 1 B square B power 3, 1 C square C power 3. And is this not same as this? Yes. What about minus 1 square? That's simply 1. And yes, this is my RHS. Did we expand the determinant at any stage? No, we never expanded the determinant at any stage. We were simply using properties of determinants and we have reached the RHS. That's a complete proof of this question over here. Is that all? Yes, that's all that you have over here. Let's discuss this next question that we have in front of us. We have cos alpha, cos beta, cos alpha, sin beta, minus sin alpha, minus sin beta, cos beta 0, sin alpha, cos beta, sin alpha, sin beta and cos alpha. We are supposed to evaluate the value of this determinant. Okay, and how do we do that? If you see clearly, there is a 0 over here, okay, that is visible, but what else? Do we have another 0 or do we have the possibility of creating another 0? Observe that cos alpha, cos beta is here as well, sin beta, cos alpha, sin alpha, this is what we have, right? So there aren't many options. One of the things is to directly, what we can do is probably expand along this one maybe. Yes, that's something which you can do, but you will see that things will not become easy. Will they be? Maybe. Sin alpha, this will become sin square beta and this will become cos square beta. Yes, that is also simple. That's not out about it. That will make things pretty simple. Let's use that idea. Another idea could have been to maybe create another 0 somehow. There's a sin alpha over here, there's a cos alpha over here. Let's try to multiply this one by cos alpha, this one by sin alpha, and then maybe add them together. That is, R1 can be replaced with R1 plus R3. And in that case, if you replace that, you'll get a 0 over here as well. Then you can expand along this column and get a simple expression over there. So which of these methods can we prefer over here? Anyone will do. Let's use the second one that we have discussed first. So let's use the second one and then we'll discuss with the first one as well, that is direct expansion. So what I'll have is delta. This delta is equal to what? This delta is equal to, what I am doing is, I am multiplying this by cos alpha and I am multiplying this by sin alpha. So if I multiply by something, I'll have to divide by something, right? So let's divide by sin alpha and cos alpha. The determinant will have, you'll multiply this by cos alpha, R1 by cos alpha. So this will become cos square alpha, okay, cos beta, okay. This will become cos square alpha, sin beta, that's also okay. The last term will become minus sin alpha is already there. You are multiplying by cos alpha, so this becomes minus sin alpha times cos alpha. Okay, what next? This is minus sin beta, this is cos beta, and this is 0. This has to be multiplied by sin alpha. right? So this becomes sine square alpha cos beta, sine square alpha sine beta, and this becomes cos alpha sin alpha. Okay, now let's add this over here. R1 can be replaced by R1 plus R3. This remains as it is. What will this become? Sum of this and this. You will observe cos beta will come out common and cos square alpha plus sin square alpha will be there in the bracket, right? Add this and this term together. So cos beta will come out common and that is what will remain, because sin square alpha plus cos square alpha in the bracket is 1. What about these two terms? When you add this term over here, cos square alpha sin beta, sin square alpha sin beta, once again you observe that sin beta will come out common. Cos square alpha plus sin square alpha will be simply equal to 1. Minus sin alpha cos alpha sin alpha will become 0. That was our target, right? That was the original target. The next two terms are minus sin beta cos beta, 0 as well again. And you have something over here, and you have a cos alpha sin alpha over here. Okay, why are you not writing those terms? Because I will not require those terms. Okay, oh, but we should write. Okay, let's write that. In that case, this is cos beta, this is sin square alpha sin beta. Expand along this column. Expansion along this column will give me this term times cross multiplication of this. This is 1 over sin alpha cos alpha times. Let's expand along this. The first term that we'll get is cos alpha sin alpha times the cross of this. What will that be? Cos square beta minus or minus will become plus sin square beta. Okay, this here is 1. Cos alpha sin alpha will get cancelled and the overall value will be 1 and 1. This is 1. The value of this determinant is simply equal to 1. That's what I get, right? That's my answer for this question. Is that okay? Yes, that's simple. Yes. We were supposed to discuss using another approach as well, right? Yes, let's do that. Let's discuss using another approach as well. What's the other approach? Okay, so we can expand directly. Why not expand directly? Let's do that. Expansion directly along maybe this column as well, right? So delta will be equal to minus sin alpha is the first term times this determinant, cross and cross. So what you'll get is minus sin beta sin alpha, which will be minus sin alpha sin square beta. This is what you'll get, right? This times this will be with a minus, cos beta will become cos square beta. There's a sin alpha and this will become cos square beta. Okay, minus 0 is gone, plus the other term will be of cos alpha. And what will that be? This is cos alpha cos square beta. Minus of minus will become plus, since there is a minus sin beta. So it will become cos alpha times sin square beta. Okay, what will this give us? Let's observe. In these two terms, you have a cos alpha coming out common. What you have is cos square beta plus sin square beta remaining, which is 1, right? Here as well, you have minus sin alpha coming out common. Minus sin alpha will become minus sin alpha square. Okay, and in the bracket you have sin square beta plus cos square beta, which is simply 1. Pretty simple. Here you have cos alpha outside, another cos alpha coming out. This will become cos square alpha, and what remains inside is cos square plus sin square, which is 1. Cos square beta plus sin square beta, which is 1. This here is nothing but sin square alpha, and this here is cos square alpha. Obviously, they will add up to give you a 1, and that's my answer for this question, as you can see behind me. Right, that's a complete question in front of you. Let's move on to the next question after this. If A, B and C are real numbers and delta is this determinant, which is equal to 0 as well, show that either A plus B plus C is equal to 0 or A is equal to B is equal to C. That's what we need to show. Okay, and how do we think we can approach this question? We can approach this question using two ideas once again. One of the ideas is, if you observe this kind of a determinant, please clearly see that this determinant can be split as sum of two determinants. Okay, sum of two determinants, yes. But sum of two determinants is not something that we have discussed with the NCERT, right? So I'll not use that idea over here. What I'll use is another idea, which is, right, which is a relatively simpler version. What's that? You try to create some ones and then maybe evaluate this and see where does that take us, right? Okay, so let's try to evaluate the value of this delta somehow. What do we have? We have B plus C plus A plus B, C plus A plus B, B plus C. We have similar kinds of terms, right? Let's add them along this, right? Well, what we'll do is we'll replace C1 by C1 plus C2 plus C3. Is that okay? Yes. So what you get is B plus C plus A plus B is simply equal to 2 times A plus B plus C. B and B will get 2B, 2C, 2A, 2 times A plus B plus C. Similarly, in the next row, you'll get 2 times A plus B plus C and 2 times A plus B plus C here as well. The 3 rows, and the 3 rows, the first column, basically this will be the first column. The next column, let it remain as it is, yes. What you'll get is C plus A plus B, this is A plus B, this is B plus C, this is B plus C, this is C plus A. Now the benefit of this, we are trying to evaluate this value is given to be 0, and on the basis of this we are supposed to show either this equal to 0 or this equals this. Now that's pretty simple considering the step that we have applied. What we can see is we can take out this factor common. Okay, so a factor times another factor, if it is 0, what we'll get is simply the first factor equal to 0 or the second factor equal to 0. The first factor, as you can see, is that A plus B plus C equals 0, that is required. That's the benefit of applying this step. Let's continue further. 2 times A plus B plus C. This particular thing implies this times you have a determinant 1, 1, 1, C plus A plus B, B plus C, and you have A plus B, B plus C, C plus A is equal to 0. Okay, life has become slightly simpler, but it is not simple enough. We are supposed to evaluate this factor as well. Okay, so where does that take us? We'll have to create some zeros over here. Yes, we'll have to create some zeros. Let's see. We can create some zeros by subtracting, right? So this will give me 2 times A plus B plus C times this. This will become 0 by subtracting with this. Okay, C plus A minus A plus B, where does that take me? This A will get cancelled. This will become C minus B. Okay. Similarly, this A, B will get cancelled. This will become A minus C. Okay. You create another 0 over here by subtracting these two. A plus B minus B plus C. This will become A minus C. B plus C minus A, we get B minus A. Okay. The last term will remain as it is. The last row, 1, B plus C, C plus A will remain as it is. This product is equal to 0. Now we'll go about expanding this determinant. Expanding this determinant will be very easy now. We'll have to expand along the first column, and that will give me this times this minus this times this. 2 times A plus B plus C is okay, times expansion would involve 1 times this minus this. What is that? C minus B times B minus A. Okay, let's multiply them. Minus A minus C and A minus C, that is A minus C whole square, this is equal to 0. That's what you're getting, right? So 2 times A plus B plus C, this is okay, times, what is this simplifying into? Let's observe what is this simplifying into. This becomes CB, okay, let us write it as BC, minus CA minus B square plus AB, okay. This is minus A square minus C square, and you have 2AC remaining over there. Minus of 2AC times minus 2AC will become 2AC in this addition. This is what you will getting, equals to 0. This is what I will be reaching. Next, this is 2 times A plus B plus C, which is okay. Let's write it as 2 times A plus B plus C, which is okay. That's not an issue. What is this bracket equal to? Can you please observe that A square, C square and B square have a minus in front of them. Let's take out a minus common first of all. And let's observe the remaining bracket. A square plus B square plus C square will come with the plus, right? Then you have BC, CA, AB and 2AC. 2AC minus CA will be 2AC minus AC, which is plus AC. So plus AC plus BC plus AB, and since you took out a minus common, what you'll get is minus AB minus BC minus CA. This is what you'll get, right? This is what you'll get. Now for students who remember this kind of an expression, you would note that this can further be written in another version, right? This can further be written as, this is minus 2 times A plus B plus C, and this further can be written as, in terms of A minus B whole square, B minus C whole square, C minus A whole square. I'll write that expression. How do we get that expression, by the way? We multiply this whole expression by 2. We multiply this whole expression by 2. This becomes 2ab. There are 2a square, 2b square. Let's take 1a square, 1b square with this 2ab. What you'll get is a square plus b square minus 2ab, which is a minus b whole square. Okay. Then you have b square, c square and 2bc. That will become b minus c whole square. Another one will be c minus a whole square. But for that, what did you do? You multiplied this whole expression by 2. Let's divide the whole expression by 2. That's this, right? And this is equal to 0. If this is equal to 0, then where does that take us? If you observe the product, this is minus 1, which is okay, but the product of this factor and the other factor is 0. This implies that the first factor a plus b plus c equals 0, or the second factor equals 0. Now what is the second factor? A minus b whole square plus b minus c whole square plus c minus a whole square is equal to 0. Observe carefully. Square is greater than equal to 0, greater than equal to 0, greater than equal to 0. Three positive terms, three non-negative terms basically when added together are giving you a 0. Greater than equal to 0, greater than equal to 0, greater than equal to 0. If you are adding them to be 0, then do you observe that each of these will have to be obviously 0. For getting the final result as 0, each of these. If this reaches, let us say by any chance, if this reaches a number greater than 1, this is greater than equal to 0, let's give this 1, right? Even if you make both of them 0, you'll still have a net output of 1 in the LHS, which is never 0, which can never be 0, right? So for that, this will be 0, this will be 0 and this will be 0. So to get RHS equal to 0. So this is actually sum of 3 non-negative numbers equal to 0. Therefore, each number will be 0. Okay. A minus b will be 0. That implies A equals b. B minus c will be 0. That implies b equals c. C equals a. A equals b. B equals c. C equals a. Which implies that a is equal to b is equal to c. This or this. That is what you get. This or this. That's what you wanted to get. Right? That's the complete proof of this question over here. That's the complete proof using simplification of determinant like this. Let me get a side so that you can take a look at the complete solution of this question. And yes, that's all for this question. Let's move on to the next one. This. Solve the equation x plus a, x plus a, x plus a. Okay. So what are we supposed to do? In such a question, it is very easy if you observe the terms are similar in a particular row or a particular column. Let's add them, right? So this implies this is equal to 0, right? I'm adding c1 plus c2 plus c3 and giving it to c1, right? So this becomes 3x plus a, 3x plus a, 3x plus a. Now we have been doing this for so long that I hope you would have felt that this is but obvious, right? This is x plus a, x plus a, and this is equal to 0. It is given, right? Now we can take out that factor of 3x plus a common. Yes. This is coming out to be common. The determinant 1, 1, 1. X plus a, x plus a is what I'll be getting. This is equal to 0. Right. Now can you create some zeros? Yes, I can create some zeros by subtracting R1 from R2 and from R3 as well, right? Let's try to do that. This gives me 3x plus a, which is okay. And the first row, 1, x remains as it is. This will become 0. R2 minus R1 will become 0, a, 0. Yes. And R3 minus R1 will also become 1, 0, a. This is equal to 0. Therefore, what I get is 3x plus a is outside, waiting outside, let it wait outside. Expand along this, what you get is 1 times a square minus 0, which is simply a square. Okay. So this implies that 3x plus a equals 0 or a square equals 0. Okay. A square 0, but a is not given 0, right? This will not give us any solution. And this here will give me x equals minus a by 3. And yes, that is my answer for this question. We were supposed to solve the equation, right? Solving the equation requires us to find the value of our variable, that is x. And we have done exactly that, right? This is a complete solution of this question. Let's discuss this question. The question says, prove that a square bc ac plus c square, a square plus ab b square ac, ab b square plus bc c square is equal to 4a square b square c square. Now, how are we going to do that? Observe that what do we have in the LHS? In the LHS we have this determinant, and before we write anything, let's observe that we can take out some factors common, right? We need factors of a, b and c over here in the RHS, right? And I see a lot of a's, lot of b's and a lot of c's over here. Let's take them out common. A, b and c. From the first column will become a plus b, b. Okay, you have taken out an a. In the second column you had b square bc, and you can take out a b common, you would remain with a c, b and a b plus c. Okay, what next? You have ac plus c square, you took out a c common, this becomes a plus c, this becomes a, this becomes c, right? This is what I'll get in the LHS. Okay, what else? Can we create some zeros over here somehow? Because can we take out any other factors? No, what extra thing is required is 4 times a times b times c, and if you observe, there will be a, b, c created over here, but then there will be a lot of extra terms, and lot of extra terms. Out of those terms, many terms will get cancelled. Okay, and some terms will get added as well. But before you actually expand, can you create some zeros somehow? Yes, maybe. If I want to expand along this, I can create a zero over here by adding this and subtracting from this. What do I want to do? I want to replace R2 by R2 minus R1 minus R3. This minus this will create a zero over here. Yes. What will happen over here? Oh, there will be some mischievous things happening over here. But then let it be. This is A, B, C, and what you'll get is A, C, A plus C will remain as it is. A plus B minus A minus B will become 0. Okay. B minus B will become 0. Minus C will become minus 2C. Is that okay? Please observe. B minus B will become 0. There will be minus C and there will be another minus C, that will become minus 2C. A minus A will become 0. Minus C and minus C will become minus 2C. Okay. B is okay. B plus C is okay. And C is okay. That's not an issue. Okay, there's a 0 over here, and there are minus 2c lying over here. Can we subtract them to get some more zeros? Yes, we can do that. Let's try to create some more zeros, or alternatively I can expand along this column as well, right? But since we can create more zeros, let's do it. This will give me LHS is equal to ABC times. What I want to do is, I want to subtract C2 and C1. What I'll get is, let's replace C3 and C2. Let's replace C3 by C3 minus C2. So C3 can be replaced by C3 minus C2. That's the step that I want to apply. The first column A, 0B will remain as it is. C2 will also remain as it is. C minus 2C and B plus C. This column A plus C minus C will remain. This is A. Minus 2c, they will get cancelled. This is 0. A minus B minus C, what will that be? Minus B will remain. This is what I am getting at the end, right? At the end of all this, this is what I am getting, and now I'll expand along this row over here. Okay, this plus minus 0 plus this minus 0. Okay, so you'll have plus times minus 2c times this. A times minus B minus this. So you'll have minus AB and minus AB over here, right? This is what I'll be getting. And what is this equal to? This is ABC, which is okay. Minus 2 and minus again common. This will become 2 times C times, this is 2AB actually. And this will be 4 times A square, B square, C square. Yes. This is my RHS, and that's a complete proof of this question. We could, mind you, we could have expanded at this stage or at this stage as well, but then creating a zeros would, at the end of the day, by creating zeros, we have converted that expansion part into a very small expression. Expansion at this stage would give you many terms. One of the terms would be ABC in plus. There will be quite a few plus terms and quite a few minus terms. The next term will be AA, B, which will be minus term, that will have to be cancelled. AAC will also get cancelled. Then you will have, this is a diagonal, ABC in a plus. Then you have A plus B, B plus C times A plus C. That term will also be there. If you observe, A plus B, A plus C, B plus C, that term will also be there, and that will be a very huge term. That term in itself, when expanded, will give you 8 extra terms. So expansion at this stage will be very risky. Even at this stage, if you observe, okay, the risk reduces by a bit, but then once you reach this stage, why not go a step ahead and create some more zeros to simplify the calculations further, right? Using this idea, you can get the solution very easily. This is question number 6 for you. That's all in this question. Let me get aside for you to take a look at the complete solution. After that, we'll move on to the next question, that is 7th. If A inverse is this matrix and B is this matrix, find AB whole inverse. Okay, so the approach that we can follow for solving this question will be, could be one of the approaches could be that we find AB first of all. Okay, so for that we'll need A and B. B is given, but A has to be found using A inverse. So we'll find the inverse of this and get A. Then we'll multiply them together to give you AB, and then you go about finding the inverse of this. That's one approach, mind you. But then there's another idea. What's that? This AB inverse is also equal to B inverse A inverse. This is something that we know. This is not something that we know from our previous concepts. And since for this one, for finding AB inverse, we need B inverse and A inverse. Do we have A inverse? A inverse is already given to us. For B inverse, we are given B. So let's find this inverse from here, and using them we can find this product, right? So one inverse and one product. Here you will find one inverse, one product, and then another inverse. Which of these processes would we like to use? We would like to use this one over here, right? One inverse and one product. If you want, you can use this one as well. The steps would be similar. You will find inverse, then you will find the product, and then you will find the inverse of AB, right? Both of the approaches are there available to you. I'll be using this over here, B to B inverse, then I'll multiply B inverse with A inverse, and I'll get this, right? This is equal to that. Given the matrix B, can I find B inverse? Yes, maybe. 1 minus 1 0, 2 3 minus 2 minus 2 0 1. This is the matrix B. Okay, and with this matrix B, what I'll require is, let's let it remain as it is. I will first check the determinant of B. Let's check the determinant of B. Determinant of B is equal to what? For checking determinant of B, I can expand along any particular row, any particular column which has zeros, or we can create some more zeros maybe. We can add this over here and we can create some more zeros. 1, 2 and minus 2 will remain as it is. This will become 0, 3 plus 2 will become 5, and this will become minus 2. This is 0, minus 2, 1, which is okay, yes, which is simple. And expansion along this will give me 5 minus 4. 1 times 5 minus 4, which is 1. Since this is non-zero, inverse will exist. Obviously, since the question is of inverse, the inverse would have existed, right? But then we have verified that determinant of B is non-zero. After this, we also require something called the cofactors, right? So that we can write the adjoint, and therefore we'll have B inverse is equal to 1 upon determinant of B times adjoint of B. Now for adjoint of B, I need the cofactors, and let's try to find the cofactors separately. Cofactors, yes, we can use this grid to find the cofactors of all the elements over here, right? This is something which I am doing in the rough. For this element, this is 3 plus 0, 3 plus 0, right? This will become 3 only. There is extra minus, don't forget that. The extra minus is over here, right? Then for this 2, you have minus 1 and 0, this will become plus 1. For this minus 2, you have 2 minus 0, which will become 2. For this minus 1, you have 2 minus 4, actually. 2 minus 4 will be minus 2, this will become plus 2. For this element over here, you have 1 minus 0, which is 1. For this element over here, you have minus 2 and 0. This will become plus 2, right? For this element over here, this is 0, and minus of minus 6 will become plus 6. For this element, you get 0 and minus 2, that will become plus 2. for this element, you get 3 plus 2, which is 5. So that's the cofactor matrix, right? This is the cofactor matrix. Adjoint will be the transpose of this. This is equal to 1 upon 1 and determinant is 1, right? The transpose of this will be 3, 1, 2, 2, 1, 2, 6, 2, 5. The first row will become the first column, second row becomes the second column, third row becomes the third column, and that's the inverse of B that was required, right? That's the inverse of B. We have found B inverse? Yes, we have found B inverse. And can I multiply B inverse and A inverse? Yes. Can I multiply these two? This is equal to this. That's something which we already know, if you know that, right? So, finding this or finding this is equivalent. For finding this, I'll try to find this first, right? Let's try to find B inverse, A inverse. Therefore, AB inverse is equal to B inverse, A inverse, which is equal to what? There's one matrix B inverse and there's another matrix A inverse. A inverse is given. B inverse is this. 3, 2, 6, 1, 1, 2, 2, 2, 5. This is B inverse times A inverse is 3 minus 1, 1. Minus 15, 6 minus 5. 5 minus 2, 2. This is what you have. And using this, I can find the product. What I'll get is, please observe. First row will multiply with the first column. 9 minus 30 plus 30. 9 minus 30 plus 30 will be simply 9. Next, minus 3 plus 12 minus 12, which will be minus 3. Next, 3 minus 10 plus 12, right? 3 minus 10 is minus 7 plus 12. Minus 7 plus 12 is 5. This is what will remain. 3 minus 15 plus 10. 3 minus 15 plus 10 is 13 minus 15, which is minus 2. Minus 1 plus 6 minus 4. Minus 1 plus 6 is 5, minus 4 is 1. 1 minus 5 plus 4. 1 minus 5 is minus 4 plus 4 is 0. 6 minus 30 plus 25. 6 minus 30 is minus 24 and plus 25 is 1. Minus 2 plus 12 is plus 10 and minus 10 is 0. 2 minus 10 and plus 10 is simply 2. This is what I'll be getting. That's the product AB and whole inverse, right? That's the answer for this question. Let us discuss this question in front of us. The question says, let A matrix is this: 1 minus 2 1 minus 2 3 1 1 1 5. Verify that. Okay, the inverse of adjoint A is equal to adjoint of A inverse. That's the first part. And there's another part, that is the inverse of A inverse is equal to A. Well, this is simple, right? And this is something which you know, that you should also remember that one. But let's verify that one for this matrix first of all. Now, how do we go about doing that? Okay, so adjoint of A and its inverse, what is that equal to? Let's observe. By the way, before I verify this one for this matrix, can you observe that this can be in general proved, right? Adjoint of A. Now, what is adjoint of A? Adjoint of A, if you may remember, can be dealt in terms of inverse as adjoint of A times determinant 1 upon determinant of A is nothing but A inverse. So, adjoint of A is nothing but determinant of A times A inverse, right? You can deal with that in this manner. What's the inverse of this matrix? What's the inverse of this matrix? For adjoint of A inverse, what we will require is determinant of A times A inverse and its inverse. Now, what is K times A and its inverse? Ka inverse is equal to something interesting, right? This is 1 upon K times A inverse. This is what we'll be getting, right? So, this will convert to what? Let's observe. By the way, is this true? Yes, this is true. And you can prove that one as well, although it will require some more steps. But then I'm not going into those details. Ka whole inverse is 1 upon K times A inverse. You can prove this with the help of that. A times adjoint of A is equal to determinant of A times In. And instead of A, you can take Ka and find the inverse and all. Let's focus on this one. Adjoint of A inverse is what I'm interested in. This is equal to this. So this is scalar times A. Scalar times a matrix and its whole inverse. A scalar times a matrix and its whole inverse will be 1 upon that scalar times inverse of this matrix. Now, A inverse is simply A. Is it not? Yes, this is simply A. This is what I'm getting. And what do we have in the RHS? We have adjoint of A inverse in the RHS. Okay, and adjoint of A inverse, what will that be equal to? So A inverse times adjoint of A inverse, this is A times adjoint of A is equal to determinant of A times I. Yes. So A inverse times adjoint of A inverse will be determinant of A inverse times IN. Let's post multiply by A and pre multiply by A. A times A inverse is I, and this will be pre multiplied. So this will be A times IN, which will be simply A. It's just pretty simple, right? What about determinant of A inverse? This is 1 upon determinant of A times A. This here is same as adjoint of A inverse. Okay, same as adjoint of A inverse, and this is what we are looking to prove, right? So we can memorize this. Yes, we can memorize this, but we are supposed to verify for this matrix that this particular result is true, and this is also true. We'll verify this. Now common link, is there any common link? Yes, we'll need A inverse, right? For finding A inverse, we'll also need adjoint of A, which will be useful over here. So let's focus on finding adjoint of A, but before that, let's check determinant of A. Okay, how do we check determinant of A? Determinant of A is not very difficult. Determinant of A can be found easily. If you observe, yes, matrix A is a symmetric matrix. Observe this, okay. Symmetric matrix is there. Can we create some zeros somewhere, somehow? Maybe we can create some zeros by, let us say, subtracting 1 and 1, adding 1 and 1 to this minus 2, will get a 0 over here. But that will be all, I suppose. Anything else? No. So instead of doing that, we can also expand directly instead of adding one step like that, which will not be very useful. Let's directly find the value of determinant by expansion. So what you get is 1 times, this is 15 minus 1 is 14. Okay, minus or minus 2 will become plus 2. Expansion along the first column. Okay, plus 2 times, what you get is minus 10 minus 1 is minus 11. Okay, next this 1 times, what you get is minus 2 minus 3, which is minus 5. Okay, and this will give me minus 5 minus 22 is minus 27, right? Please check that. And 14 is minus 13. Since this is non-zero, implies A inverse exists. This is something which we know, right? And we need to find A inverse at a lot of places. For that, we'll need adjoint of A. Let's find adjoint of A as well. Adjoint of A is actually the transpose of the cofactor matrix. This is a transpose of this matrix. Let's write the cofactor matrix. That grid we have been following, we have been making. Let's write the values directly in this matrix form. And what do we get? This is 15 minus 1, which is 14. We have used that, right? For this, we have minus 10 minus 1, which is minus 11. For this, we have minus 2 minus 3, which is minus 5. And since this is a symmetric matrix, you will get similar values over here, minus 11 and minus 5 here as well. Let's check. This is minus 10 minus 1, which is minus 11. Oh, just a minute. These are cofactors, right? So there will be an extra minus. This will become plus, right? Remember that. For this element, you get minus 2 minus 3, which is minus 5c. Okay. And then there will be 2 minuses extra over here as well. What about this element? This is 5 minus 1, which is 4. Okay. Next, you have, for this element, you have 1 plus 2, which is 3. This becomes minus 3. This will also become minus 3. For this element, you have 3 minus 4, which is minus 1. And yes, by the concept of symmetricity, we can say that the transpose will also be that same matrix, 14, 11, minus 5, 11, 4, minus 3, and then you have minus 5, minus 3, minus 1. Can you observe that? This is the adjoint of A. This is the adjoint of A. Okay. We have found determinant of A, we have found adjoint of A, and therefore A inverse is very easy. A inverse is nothing but 1 upon determinant of A times adjoint of A. Therefore, A inverse is equal to what? That is 1 upon determinant of A times adjoint of A, which gives me A inverse is equal to minus 1 by 13 times this matrix, which is 14, 11, minus 5 and 11, 4, minus 3, minus 5, minus 3, minus 1 is what I get over here. This is my A inverse. Okay. If you observe carefully, in the first part, we don't need any of this. We don't need the inverse of A. We need something else. We need the adjoint of A inverse, and we need adjoint of A and its inverse. Okay, we are interested in both of these things. Let's go ahead and solve that. Let's go ahead and find those values. Let adjoint of A is equal to another matrix P. And we are interested in the inverse of P. And how do we go about finding that? For finding that, we need the determinant of P. Yes. And what's the determinant of P? Therefore, determinant of P is equal to what? For this matrix over here, we are supposed to find the determinant. And you may see this is again having a similar problem like the determinant of A, right? We should directly expand this. Let's do that. This is 14 times, what you get is minus 4 and minus 9, which is minus 4 minus 9 is minus 13. Okay. Then you have minus 11 times minus 11 and 15, minus 15 actually. Minus 11 minus 15 will be minus 26. Okay. Then you have minus 5 extra, and with that you have minus 33 plus 20, minus 13 is what remains. What will this simplify into? 14 times 13. That is 14 times 13 is 182 minus 182 is what I'll be getting. What about this plus? This 26 times 11. 26 times 11 will be 17, and 16 times 1 is 16, 17. This is basically 260 and 26, 286. And you have plus 65. What do you have? 286 minus 182 is 104, and 165 will be 169. Since this is non-zero, therefore inverse exists. And for finding the inverse, let's find the adjoint of B first of all. So adjoint of B is something which I am interested in. Now, being a symmetric matrix, we know that the transpose will be same as the matrix itself. So let's find the adjoint of B directly. B is this adjoint of A. For that, I need the cofactors of these elements. For 14, you have minus 4 minus 9, which is minus 13. For 11, you have minus 11 minus 15, which is minus 26, but an extra minus will make it 26. For minus 5, you have minus 33 plus this is just minus 13. Right? And a similar values will be found over here. This is 26, this is minus 13. Right? That's adjoint of B. We are finding adjoint of B. Minus 14 and minus 25. Minus 14 minus 25 is minus 39. Let's keep an extra minus over here. Find this. This is minus 42 and minus 42 and minus 55 plus 55. 55 minus 42 is 13. 13 with an extra minus will make minus 13. Same term will be here since matrices are symmetric, right? 14 times 4 is 56 minus 121 is what will require. 56 minus 121 is 44 and 21. 65, right? This is what I'll be getting. Check that again. 121 and sorry, this is 56 minus 121. Okay, 56 minus 121. So 121 minus 56 will be 44 and 21, 40, 50, 60, 65. Minus 65 is what I'm getting over here. This is adjoint of B. Determinant of B is already there. Adjoint of B has been found. Therefore, B inverse, which is actually adjoint of A and its inverse is equal to determinant of B in the denominator and times 1 upon this. This is 1 over 169 times this matrix. What is this? Minus 13, 26, minus 13, 26, minus 39 and minus 13. Then you have minus 13, minus 13, minus 65. Okay. And can we take out a factor of 13 common from all of these elements? Yes, we can take out a factor of 13 common from all of these elements. Therefore, what I'll get is this. Let me write the final step after this. This will give me B inverse, which is adjoint of A whole inverse is equal to what? We've taken a 13 factor. You observe all of these have a factor of 13. 13 upon 169 will become 1 over 13 times this matrix. What is this? Minus 1, 2, minus 1. 2, minus 3, minus 1. Minus 1, minus 1, minus 5. This is what I'll be getting, right? So, at the end of all of this, just the one thing has been found, that is adjoint of A whole inverse. But we are very close to finding this one as well. We have already found A inverse, right? We have found A inverse. And with A inverse, we are supposed to find adjoint of A inverse first of all. Okay. let's go about finding adjoint of A inverse. Using that A inverse, we can find adjoint of A inverse very easily. What will that be? Okay, so you have minus 1 by 13 outside, yes, let that remain outside only. Now with this minus 1 by 13, what do? Let's observe, adjoint of A inverse will be actually cofactors, right? Cofactors. So this minus 1 by 13, since it is a scalar quantity, finding the cofactors will have to multiply this throughout with each and every element, and then we find the cofactors, right? After that we'll take the transpose. This symmetric matrix, so taking the transpose will not have much impact, but this minus 1 by 13, if it is multiplied to this and this, what we'll get is 4 minus 1 will have minus 1 by 13, minus 1 by 13, and these will get multiplied together, right? So we'll get 1 by 169 throughout, that is minus 1 by 13, minus 1 by 13 product along with these numbers, right? So can I take that 1 by 160 minus 1 by 13 whole square outside from the very beginning? Yes. So this will be 1 minus 1 by 13 whole square, which is 1 by 169 times the adjoint. What will that be? For this element you get minus 4 minus 9, which is minus 13, right? For this element you get minus 11 and minus 15, which is minus 26, and there is an extra minus, therefore this becomes 26. Similar term will be over here. For this you get minus 39 minus 33 and plus 20, which is minus 33 plus 20 is minus 13. Okay, pretty interesting. And what else? A similar term will be over here. Next, for this element over here, this element, minus 14 and minus 25 is minus 39. This is what I'll get over here. Next, for this element, what do you get? This element is minus 42 and plus 55. 55 minus 42 is 13, but there's an extra minus that will give me minus 13 over here. And similarly minus 13 over here. For this element you get 14 times 4 is 56 minus 121. Oh, we did a similar calculation sometime, right? This was minus 65, right? And if you divide by 13, what you get is 1 by 13 times minus 1, 2, minus 1, 2, minus 3, minus 1, minus 1, minus 1, minus 5. This is what I'll be getting. And do you observe carefully that adjoint of A inverse is equal to adjoint of A whole inverse is equal to adjoint of simply A inverse. This and this are exactly same. Please observe minus 1, 2, minus 1, 2 minus 3, 1, minus 1 and minus 1, minus 1, minus 5. Therefore, we can say that adjoint of A whole inverse is equal to adjoint of A inverse is what we have proved, hence verified. This is something which we have verified, right, for this matrix over here. Is that okay? Yes, that's okay. That's something which we have verified. Next part, for the next part, we already have A inverse, right? The next thing that we need is the inverse of that. Okay, we already have the value of A, and for inverse, the inverse of inverse, we need adjoint of A inverse, right? And let's find that first. The next thing is we are interested in the inverse of inverse. Okay, let A inverse is equal to C. Okay, and therefore determinant, let's find the determinant of this first. Yes, we'll have to find the determinant of this first. Determinant of C is equal to what? Now that will be a long affair. Okay, but as you may clearly observe, this is K times some matrix, right? K times some matrix, and if you want to find the determinant, that will be equal to K power the order, this is K power 3 minus 1 by 13 power 3 times the determinant of that remaining matrix, and that can be found easily using a basic ideas. What is that? 14 times this is minus 4 and plus this. Actually, have you found that determinant somehow? Yes, we have found this value over here, and this is the value that I am getting, which is 169. Are we getting this value? Yes. Adjoint of A is this particular thing, and if this is B, this is determinant of B, which is equal to 169 over here. This is something which we have found. Let's use that. This is 1 upon 13 power 3. This is minus 1 over 13 power 3, and this is 13 power 2, which is minus 1 by 13. Minus 1 by 13. Since this is non-zero, therefore inverse will exist. Okay, and for finding the inverse, therefore C inverse is 1 upon determinant of C times what else? We'll need adjoint of C. Okay, and C inverse is actually the inverse of inverse, which is equal to 1 upon determinant of C, which is 1 upon minus 1 by 13, which becomes minus 13. Adjoint of C is nothing but adjoint of A inverse, and have we found that? Yes, we have found that adjoint of A inverse over here. This is the value, and this is equal to 1 by 13 times this matrix over here, which is minus 1, 2, minus 1, 2, minus 3, minus 1, minus 1, minus 1, minus 5. Okay, let's write that again. This implies that A inverse and its inverse is equal to minus 1 times this whole thing. Let's multiply that minus inside, and what do we get? 1, minus 2, 1, minus 2, 3, 1, 1, 1, 5 is what I'll be getting over here. And this is supposed to be equal to A. Is this equal to A? 1 minus 2, 1, minus 2, 3, 1, 1, 1, 5. Yes, this is equal to A, hence verified the other one as well. This is for the second one. This is a proof of the second one as well. We've solved from here to here. We've solved the first one, and this is the second one, second part of the same question, of question number 8, as you can see behind me. Let me get aside for a bit so that you can take a look at the complete solution. And yes, that is all that you have in this question over here. Let's discuss this question next. The question says evaluate x, y, x plus y, y, x plus y, x plus y, x, y. We're supposed to evaluate the value of this expression. How do we go about doing this one? We have solved some questions similar to this. Okay, and as you may clearly see that if you directly expand, you'll get this product somewhere, x plus y times x plus y times x plus y. That will be long, right? Instead of getting that product, let's try to create some zeros somehow. Delta is equal to this. Can we create some zeros? Yes, we can add these two and subtract from here, and we'll create a zero over here. So the transformation that I want to apply is R3 replaced by R3 minus R1 minus R2. And what will that give me? X, y is okay. X plus y minus x minus y will become 0. Y, x plus y is also okay. This minus this will become minus 2y. Observe carefully, yes. This minus this, my y minus y will get cancelled, minus minus will become minus 2x. This x and x plus y will remain as it is. And what else? After this, can we create some more zeros over here? Now, if you observe, this is 2y and 2y. At max, what you'll get is this kind of a term. Can we create some more zeros? No, it's not actually possible to create more zeros without affecting in one particular row or column. Can we create zeros over here? No, it's not possible. Can we create zeros over here? No, it's not possible directly. At max, we can create some more zeros, but that will be long in itself, right? We can also simplify by taking the difference over here, right? We can simplify by taking the difference over here. This will become y, this will become minus x. But that's it, that's it. So instead of doing any of those things, we can directly expand as well. Let's expand along the first column now. Oh, we could have expanded here as well, but then here the term that you will be getting is x plus y whole power 3. That will be pretty long. In this case, the max term that you will be getting is x plus y, which is 0 actually, x plus y whole square. You will not get any of those terms. At max, you will get 1 x plus y times another factor. That's pretty simple now. So this will become x times, what you get is this, minus 2x times x plus y, okay, and minus of this, minus of minus 2y, which will become plus 2y times x, which is 2xy. This is what I'll be getting. This is the first term. Minus y times the second term, this is minus 2xy, okay, and other than that, this is what you'll get, this into this. Please observe, plus 2y times x plus y. This is what you'll get. Right. Can we simplify this further? Yes. Minus 2x square minus 2xy plus 2xy. This is x times minus 2x square minus 2xy plus 2xy, and in this bracket these terms will get cancelled, right? This is minus y. What about this? This is minus 2xy plus 2xy plus 2y square. Yes, minus 2xy, right, plus 2xy. This will get cancelled, and this becomes minus 2x power 3. Okay, this becomes minus 2y power 3. This is the answer, or you can take out a minus 2 common. X power 3 plus y power 3 is my answer for this question. That's the value of this expression, this determinant over here. Minus 2 times x power 3 plus y power 3. Is that all? Yes. Moving on to the next one after this. This is the next one. That says 1xy, 1 x plus y, 1 x and x plus y. Can we simplify this? Yes. There are a lot of ones. Yes. Let's subtract to create some zeros over here. So delta is equal to what? So let's keep this 1 x and y as it is and subtract. This becomes a 0. X plus y minus x will become a y. Okay. Y minus y will become a 0. 1 minus 1 will become a 0, x minus x will become a 0, x plus y minus this will become an x over here. This is what I get. And on expanding along the first column, what you get is 1 times xy minus 0. Other terms are 0, this is simply xy. And yes, that is the answer for this question over here. That's simple. Yes, that's pretty simple over here. Let's move on to the next one. This one. Using properties of determinants in exercises 11 to 15, prove that this is equal to this. How do we go about solving this one? We have alpha, beta, alpha square, beta square, gamma, gamma square, beta plus gamma, gamma plus alpha, alpha plus beta. And if you observe, you have alpha minus beta, beta minus gamma, gamma minus alpha as factors. So we'll try to create those factors somehow. Yes. Another thing that I observe is alpha plus beta plus gamma. Where do I get alpha plus beta plus gamma? If I add these three, you get alpha plus beta plus gamma into 2. But here you will have alpha square plus beta square plus gamma square. That does not have a factor of alpha plus beta plus gamma. So let's not worry about this factor initially. Let's worry about the other three factors initially. Okay. So we begin with the LHS. In the LHS, you have alpha, beta, gamma. Let's subtract and create alpha minus beta. So R1 minus R2 is alpha minus beta. This is alpha square minus beta square. Beta plus gamma minus this is beta minus alpha. Okay. Next, R2 minus R3 can also be done, and this will become beta minus gamma, beta square minus gamma square, and gamma minus beta. Okay. This is gamma, gamma square, alpha plus beta simply. Observe, in the first row, you get alpha minus beta. Here you will have alpha minus beta times alpha plus beta, from which we can take out alpha minus beta common. This is also alpha minus beta, right? So I take out a factor of alpha minus beta easily from here. And what remains is 1, alpha plus beta, and this will be minus 1 simply. Similarly, in this row, you have a beta minus gamma coming out common. This is 1, this is beta plus gamma, this is a minus 1, and what else? You have gamma, gamma square, alpha plus beta. Okay. What can I do next? I can simply create some more zeros by maybe adding this over here. Yes, that's a simple approach. Let's add that and get a 0. So this will give me equal to alpha minus beta is okay. Beta minus gamma is also okay. And this determinant will be equal to 1, 1 gamma, which is okay. Alpha plus beta, beta plus gamma, and gamma square. What you'll get is minus 1 plus 1 0, minus 1 plus 1 0, 0, yes. Alpha plus beta plus gamma, yes. And now I can expand along this column, 0, 0, alpha plus beta plus gamma times this minus this is what I'll get. Alpha plus beta plus gamma times this minus this, beta plus gamma minus alpha minus beta. What will that be? Gamma minus alpha. And that is my RHS. That's a complete proof of this question over here. Using properties, we have proved this 11th one, as you can see behind me. Is that all? Yes, that's all that you have in this question. Let's discuss this question in front of us. The question says, using properties of determinants, we have to prove that this determinant is equal to this expression over here. Now, how are we supposed to do that? Observe carefully, observe carefully. There's a 1 plus p x y z, x minus y, y minus z, z minus x. Now, this is some kind of a circulant, right? Resultant of some circulant. Okay, we have x square, y square, z square, but all of these terms are actually sum of two terms. Yes. So can I split my determinant, right? Can I split my determinant as this? In the LHS, this step, now this step is very, very important. Please focus on this step. I have x square and 1 plus p x power 3. Similarly, y square, 1 plus p y power 3. And z square, 1 plus p z power 3. okay, and I want to write it as this. Please observe carefully. I want to write it as sum of two determinants, okay. The important thing is for writing it as sum of two determinants, at least two rows or two columns. Basically, you can split along a row or a column, single row or column. The other two columns should remain as it is. X square, y square, z square. If they remain as it is, then this third column, each term can be split as sum of two terms. 1 plus p x power 3 p y power 3 p z power 3. I can write this whole thing as sum of two determinants in this manner, like this. Okay, and what's important after that? Please observe, if I write it as this, then this will remain as it is. Let's not worry too much about this one. But this here, observe this one. Can I take out x common from here, y common from here, and z common from here? Not only that, can I take out a p common from here? Yes, I can do that. So this becomes, okay, this becomes, observe, can I interchange this one and first column and the third column as well? Why do I want to do that? Because I want to create a 1 over there. Okay, 1 and this will become x, y, z. This will remain x square, y square, z square. Interchanging two columns will introduce an extra minus sign over here. Yes, this is what I get. So this becomes equal to this. Plus, as I just mentioned that you can take out a x, y, z common, and what will remain is 1x p x square, 1y p y square, 1z p z square. Okay, so what's so special in this? Another thing, I can take out a p common from here, and if you observe, I have 1x and x square remaining. This can also be converted into by interchanging C2 and C3. Yes, I'll get an extra minus by interchanging them. This is 1 this will be x, y, z. This will be x square, y square, z square. Okay, extra minus will imply this becomes a plus. Okay, you have p also coming out. This is p x, y, z. And the remaining thing that you get is 1x, x square, 1y, y square, 1z, z square. Yes. Now you observe this determinant exactly same. You can take out that determinant common. Here's a 1, here's a p x, y, z. This becomes 1 plus p x, y, z times this determinant over here, which is 1 x, y, z, x square, y square, z square, and you know how to solve and find this value. You may also remember this value. This is nothing but x minus y times y minus z times z minus x. Now how do I find that value? I can find that value separately. Let's do that. Let's find this delta separately. 1 x, y, z, x square, y square, z square. We'll create some zeros, right? We'll create some zeros. Let's do that. This is 0, this is x minus y, this is x square minus y square. 0, y minus z, y square minus z square, 0, z, z square is what I get. You can take out x minus y from the first row, y minus z from the second row. Yes, and then you can expand along. By the way, this is 1, this is not 0, this is 1 over here. And then you can expand along the first column. What you get is 1 times this minus this. X minus y is gone, this is y plus z. So y plus z minus x minus y is what I get. This is gone, this is z minus x. X minus y, y minus z, z minus x is what I get. This becomes equal to 1 plus p x y z times x minus y, y minus z, z minus x is what I get. And yes, that's the complete proof of this question over here. You can take a look at the complete solution. I'll get aside for a minute, and that's all that you have in this question over here. Let's move on to the next one after this. 13th. Let's try to solve this one. The question says, using properties, prove that this is equal to this. Okay, and what kind of factors do we have? We have a plus b plus c over here. We also have 3 and ab plus bc plus ca. Okay, these will be created by multiplying maybe, and this factor has to come out common somehow. Let's focus on that. So this is a minus a minus b plus c. I can add to 3 and I get a plus b plus c over here. Similarly, I have similar things over here. In the LHS, what I can do is I can replace C1 by C1 plus C2 plus C3, and on doing that this becomes A plus B plus C. This also becomes A plus B plus C, and this becomes 3C minus C minus C is C, and A plus B, this becomes A plus B plus C as well. What do you have extra is minus A plus B, 3B, and minus C plus B. What else? Minus A plus C, minus B plus C, and 3C. This is what you have over here. Is that okay? Yes. Okay, once you have noted this, you can take out an A plus B plus C. Take out A plus B plus C. This factor common. You get 1, 1, 1 over here. Yes. We can try to create some zeros with the help of this, but will that help us? Maybe, maybe, may not be. Let's see. Can we actually create some zeros? By the way, this is 3B, this is 3C. At max, we'll have to divide by 3 and then subtract from this. You'll get minus A. You'll not get a 0. Okay, so maybe we'll think in other terms, maybe directly expanding. Let's see. Minus C plus B, minus A plus C, minus B plus C, and 3C. This is what I'm getting. Okay, at this stage, once again, at this stage, can you get some zeros somehow? No, we are not getting any zeros directly. Can we? This is 3C. You will be remaining with minus A and minus B. You will not be able to cancel them. At max, minus A can cancel, but C and B will remain, right? So subtraction will not give us anything since we want to create zeros. Oh, zeros will be created over here. Yes, zeros will be created over here in this particular column. That is possible. That is very much possible. Some expressions will be created over here. We can do that. This is A plus B plus C, and let this remain as it is. Okay, let this 1 times minus A plus B remain as it is. Okay, 1 times minus A plus B minus A plus C remains as it is. This becomes a 0. R2 minus R1 is what I am doing. 3B minus A and minus B is actually 2B plus A. Minus B plus C and minus C will go minus B plus A. This becomes A minus B actually. Is that okay? R3 minus R1 will become a 0. This minus this will be minus C plus A. This becomes a minus C. This here 3C plus A and minus this will become this. A plus 2C actually. This becomes A plus 2C. Okay. Now that is simple enough. We can expand after this. And where does that take us? This implies A plus, this is equal to A plus B plus C times this expansion 1 times this whole product. So that is equal to 2B plus A plus 2B times A plus 2C minus of A minus B, A minus C. Okay. And what does it simplify into? Let's see. Let's see. What does that simplify into? Let's multiply them. A square, okay, plus 2AC plus 2AB plus 4BC, 2B times 2C. And you have minus A square, minus AC will become plus AC, minus AB will become plus AB, and plus BC will become minus BC. This is what you have over here. Do some terms get cancelled? Yes, A square will go. And you want to see that we want to reach this AB plus BC plus CA. Let's see what are the terms that we have. So 4BC minus BC will be 3BC. AC plus 2AC will be 3AC. 2AB plus AB will be 3AB. So this becomes, yes, A plus B plus C times 3AB plus 3BC plus 3CA, and you can take out a factor of 3 common and you get this. That's a complete proof of this question, as you can clearly see behind me. Is that all? Yes, that's all that you have over here in this question. Let's move on to the next one after this. The next question says that using properties, we have to prove that this is equal to 1. How do we go about proving that? Let's take a look at this question. In the LHS, we have this determinant 1, 2, 3, okay, and you have 1, 3, 6. Along with that, you have P, 2P in plus 3P, okay. You have 1, 4, 10, but plus some things extra are also there. What is that? Let's see, this is 1 plus 4 plus this, P plus 3P plus 6P, okay, 1, 3, 6, and Q plus 2Q plus 3Q. And the important thing to observe over here is this 1, 2, 3 have been multiplied by Q added over here, multiplied by P added over here. So we can actually subtract them, yes. C2 can be replaced by C2 minus P C1. C3 can be replaced by C3 minus P minus Q times C1, right? Minus Q times C1 actually. This is what you can do. And the benefit of this will be that this will remain 1, 2, 3. But this C2 will be transferred. P times 1 will be subtracted. 2P, 3P will get subtracted. This is 1, 3, 6. What else? 1 plus P, Q gets subtracted. 2Q and 3Q will also get subtracted. And I hope you get the idea. The next step, what you will do is, you will remove these terms using this 1, 3, 6, multiply by P and subtract over here. So, the next thing that you will do is C3 will be replaced by C3 minus P C2. And this will give me 1, 2, 3, 1, 3, 6. And you will be left with 1, 4, 10. Okay, what else? Let's subtract and create some more zeros using the ones in the first row. So, what you will have is 1, 2, 3 is okay. Subtract these two. 1 minus 1 is 0, 4 minus 3 is 1, 10 minus 6 is 4. Subtract these two. This is 0, this is 1, this is 3. Okay, and after that you can expand along the first row. What you get is this times 4 minus 3. 4 minus 3, which is 1. And that is the RHS. That's the proof of this question. A simple question? Yes, a pretty simple question, considering if you can observe this. Right, that's all that you have in this question. Let's move on to the next one after this. Using properties sin alpha, cos of alpha plus delta, cos of beta plus delta, cos of gamma plus delta. Okay, and we are supposed to prove that this is equal to 0. Let's try to do that. In the LHS, we have determinant delta, sin alpha, sin beta, sin gamma. Then you have cos alpha, cos beta, cos gamma. This, let us expand this. Cos alpha plus delta will be equal to actually cos alpha, cos delta minus sin alpha, sin delta. If you observe, deltas will remain same. This is cos alpha, cos delta actually. This is not this, this is cos delta. Right. So, cos delta and sin delta will remain same in all the remaining terms. You have cos alpha and minus sin alpha. So, if I multiply this with sin delta, sin alpha, sin delta and add over here, you will get, this term will get cancelled. If I multiply this with cos delta and subtract from here, this term will also go. Okay, this term has to be added, this term has to be subtracted, and I will get a 0 over here. What about the remaining terms? Will I get similar thing over here? Yes, maybe. This is cos beta, cos delta minus sin beta, sin delta. Okay, similar terms. This is cos gamma, cos delta minus sin gamma, sin delta. Right. And now observe, I want to replace C3 by C3 plus sin delta times C1 minus cos delta times C2, and that's an important step. Yes, the moment you do this, this sin alpha, sin beta, sin gamma will remain as it is. Cos alpha, cos beta, cos gamma, the second column will remain as it is. But what about the third column? Let's observe. This plus sin delta times this, sin delta times this, sin delta, sin alpha, add over here, this term will get cancelled. Similarly, sin delta, sin beta, add over here, get cancelled. Sin delta, sin gamma, add over here, get cancelled. But you have a subtraction also. Cos delta times C2, cos delta, cos alpha, subtract from here. So, this term will go. Cos delta, cos beta, this term will go, this term will go, and what you will get is 0, 0, 0. All elements of a particular column are 0. Therefore, the value of the determinant is simply 0. Expand along this and you get a complete 0. This is the RHS, and that's the proof of this question. Simple application of trigonometry over here in determinants. Yes, that's all that you have in this question. Let's move on to the next one after this. 16th, solve the system of equations. How do we solve the system of equations? 2 by x, 3 by y, 10 by z equals 4. 4 by x minus 6 by y plus 5 by z equals 1. 6 by x plus 9 by y minus 20 by z equals 2. Okay. So, these are equations in terms of, are they in terms of x, y, z? Yes. But will we solve them in terms of x, y, z? No. Well, observe that 1 by x is our variable, 1 by y is our variable, and 1 by z is our variable. So, we will solve them in terms of 1 by x, 1 by y, 1 by z. Let 1 by x equals u, 1 by y equals v, 1 by z equals w. So the system of equations that you have will be 2u plus 3v plus 10w is equal to 4. Then you have 4u. Yes, this will be 4u minus 6v and plus 5w is equal to 1. Then you have 6u, 9v, 20w minus 20w is equal to, on the right hand side you have a 2. Okay. For this system of equations, can we create the coefficient matrix very easily? Yes. Let A equals this 2, 4, 6, 3 minus 6 and this is 9 over here, 9, 10, 5 minus 20. Let this A be this, comma, X be this matrix U, V, W and B be the matrix of the coefficients on the right, constants on the right hand side, 4, 1, 2. Therefore, Ax equals to B is the system of equations. And for solving the system of equations, we'll have to check whether determinant of A is 0 or not. So let's find determinant of A. Determinant of A can be found very easily by expanding, yes, by direct expanding. Yes, I can expand directly, maybe 2 times. What you get is this over here. 6 times 20, 120 minus 9 times 5 is 45. 120 minus 45. Okay, and then you have minus 4 times this term. Minus 60 minus 90 and then you have plus 6 times the other term. What is that? This is 5 times 3 is 15 plus 60 is what I get. This is 120 minus 45. What will that be? This is 75 and 75 times 2 is 150. This is minus 150 and minus 4 multiplied together will be 600. And what is this? This is actually 75 times 6 with a plus. This is 150 times 450 over here. Okay, so this will become 600, 600, 1200. And since this is non-zero, therefore unique solution exists. You will get a unique solution. Determinant is non-zero, therefore you get a unique solution. Solution will be x equals A inverse B is the unique solution, and for that I need A inverse. For finding A inverse, I need the adjoint of A. So let's try to find the adjoint of A. Adjoint of A will be this matrix formed using the cofactors. So let's begin with this 2. For this 2, you have 120 minus 45, which is 75. Okay, this will be 75 over here. And for this element, you will have minus 80 and minus 30, which is minus 110, that will become plus 110. But for that element, you will write 110 over here, since adjoint A is the transpose of the cofactor matrix, right? For this element, you get 36 and plus 36, which is 72. Yes, 72 will be written over here. Don't make a mistake in that. Next, you have a 4 over here. This is minus 60 minus 90 is minus 150, but that will be a plus 150 over here. Okay. What about this element? This element will be minus 40 minus 60, which will be minus 100, and this element will be here only, right? Transpose. What about this element? 18 minus 18 will be actually 0, but that will be written over here, right? For this element, what you get is 15 plus 60, which is 75, and that will go over here. For this element, you get 10 minus 40 is minus 30, but that will come over here with a plus 30. For this element, you get minus 12 is minus 24. This is what I get, right? You can also check the solution if you want. And how will we check that? We'll find the adjoint once again, since we did not use that grid and all. Let's check the values. So for this, we'll have check this. This is okay, 120. 20 times 6 is 120 minus 45, which is 75, which is okay. Okay, what about this one? This is minus 80 and minus 30, which is minus 110, that will become 110. For this, you get 9436 plus 36 is 72, which will come over here. For this, you get minus 60 and minus 90, which will be minus 150, so 150 should go over there. For this, you'll have 15 plus 60, which is 75, that will go over there. Okay, what about this element? This is minus 40 minus 60, which will be minus 100. This will be minus 100. This is not 100. This is minus 100, right? Okay, let's check that. This is minus 40 minus 60, which is minus 100. What else? This one. For this one, let's check this one. This is 10 plus 10 minus 40, which is minus 30. That becomes a 30. What about this one? For this, check this one. This is 18 minus 18, which is gone 0. Last one is minus 12. Minus 12 is minus 24. That's okay. This is minus 100, right? Take care of that. Now, once you have found adjoint of A, next what we are supposed to do is, therefore, x is equal to 1 over determinant of A times adjoint of A times B. Okay, which gives me this matrix over here, U, V, W is equal to 1 upon 1200. Determinant of A is 1200, right? Yes. Times adjoint of A. Adjoint of A is 75, 110, 72. 150 minus 100, 0. 75, 30 minus 24 times the matrix B. Now, what is the matrix B? Matrix B is this matrix 412 over here. Let's multiply them together, and where does that take us? This is 1 upon 1200. Okay, and this here is nothing but U is 1 by X, 1 by V, sorry 1 by Y, 1 by Z is what I get. This is 1 by 1200, and let's multiply them together. 75 times 4 is 300 plus 50 and plus 150 plus 150 is 600, right? Next, you have 440 minus 100 plus 60. 440 minus 100 is 340 plus 60 is 400. 144, 0 and minus 40. 72 times 4. 72 times 4 is not 144, it is 288. 288 minus 48. 288 minus 48 is 240. This is what I will be getting. What is this? Giving me 600 upon 1200 is 1 by 2, 1 by 3, and this is 1 by 5. Comparing with this, therefore, x equals 2, y equals 3, z equals 5 is my answer for this question over here, as you can clearly see behind me. Right, that's a complete solution of this question. Let's move on to the next one after this. This one. Choose the correct answer in exercise 17 to 19. Okay, 17. These are objective questions. So let's see, if ABC are an AP, then the determinant this is equal to what? Okay, so observe, you have XXX 2, 3, 4, XXX 3, 4, 5, XXX 2A, 2B and 2C, and ABC are an AP. Okay, ABC are an AP. So A plus C will be equal to 2B. That's something that's there. 3 plus 4, 5 and 2, 3, 4. Yes, this is the question that we have. And how do we solve this question? So, we have x plus 2, x plus 3. If you observe, let's try to create some zeros if possible. But let's try to eliminate the x first of all. How many x's are there? There are so many x's, right? So, delta is equal to this, and what can we do? Okay, x plus 2, x plus 3, x plus 4. What I can do is I can subtract maybe R3 minus R3 minus R2. That's okay. Yes, 4 minus 3 will become 1. 5 minus 4 will also become 1. And this is 2C and 2B. This becomes 2 times C minus B. Okay. What else? 3 minus 2. Again, I create a 1 and a 1 over here. I can subtract them and create a 0 as well, right? So that is okay. This becomes 2B minus 2A. 2 times B minus A. And what is this? This is x plus 2, x plus 3, x plus 2A. Yes or no? Yes. And maybe I can create some more zeros. Yes, I can create some more zeros over here using this idea. That is this. Let's subtract. X plus 2 is okay. X plus 3 is okay. This is x plus 2A is also okay. 1, 1, 2 times B minus A is also okay. This becomes a 0. This becomes a 0. 2C minus 2B and minus 2B. This becomes 2 times C minus 2B plus A. Okay. And what is this equal to? Please observe, if ABC are in AP, A, B, C in AP implies that A plus C will be equal to 2B, or you can say that A minus 2B plus C will be equal to 0. So this is 0. Okay. This is 0, this is 0 and this is also 0. All elements in the third row are 0. Therefore, delta is equal to 0. And was this that was asked? Yes. We are supposed to find the value of delta, and this determinant comes out to be 0. That's the option A. The correct option is option A. That's all that you have in this question over here. Let us move on to the next one after this. This one, choose the correct answer. If x, y, z are non-zero real numbers, then the inverse of matrix A is equal to what? Okay, for a diagonal matrix, although if you remember very well, then you can always say if A is this x, y, z, 0, 0, 0, 0, 0, 0, you can have A power n as x power n, y power n, z power n, and this is also true for inverses. This is also true in case of inverse. A inverse is also equal to x power minus 1, y power minus 1, z power minus 1, 0, 0, 0, 0, 0, 0. You want, you can check that. How do we check that? A times A inverse is equal to this. X 0, 0, 0, y 0, 0, 0, z. This is matrix A, and the possible matrix X inverse is X inverse 0, 0, 0, y inverse 0, 0, 0, z inverse. Let's multiply them together. The first row and the first column will become x times x inverse, which is 1. Second row, second column will become 1. Third row, third column will become 1. What about the first row and the second column? X times 0, 0 times y inverse 0, 0. Rest all terms will be 0, 0. This is identity matrix. If A times another matrix is identity, that matrix is supposed to be the inverse, and inverse is unique, therefore that is the inverse. The correct answer, as you may recall, as we can see, is this option A. Is it? Yes, x inverse, y inverse, z inverse, right? There's inverses are here also, but there's an x, y, z over here. No, that's not required. This is what is required over here, right? And what's the value of this matrix, by the way? The value of this matrix is x, y, z. Determinant of A, sorry, the value of this determinant is x, y, z, and inverse exists only when these are non-zero, right? When it is a non-singular matrix, x, y, z are given to be non-zero, therefore inverse will exist, and A is the correct answer for this question using this idea. We can remember these things. Yes, we can remember these things for a diagonal matrix, right? Remember that. Let's move on to the next one after this question. 19th says let A equals 1 sin theta 1 minus sin theta 1 sin theta minus 1 minus sin theta 1, where theta lies from 0 to 2 pi. Okay. Then determinant of A, determinant of A, determinant of A. The values of determinant of A lie in which interval? So let's try to find that. Determinant of A is equal to what? Do you observe, had these been zeros, you would have obtained a skew symmetric matrix, but these are not zeros. The diagonal elements are not zero. Okay, at max this is a sum of skew symmetric and identity matrix. But let's see, can we create some zeros somehow? Yes, we can create some zeros by adding this and this and this. Right, so determinant of A will be 1 sin theta 1, okay, minus sin theta 1 sin theta, and you add R3 plus R1, that is 0, 0, 2, and expand along this. So 2 times 1 plus sin square theta is what I get. Is that okay? Please observe, this is what I will be getting. 2 times 1 plus sin square theta, this is what I'll get. This is determinant of A, and since theta belongs to 0, 2 pi, that's the complete interval, therefore sin square theta. Sin square theta will belong to which interval? This will be from 0 to 1. Since this is square, right? So all the negative values will be converted to positive. This will lie from 0 to 1. And 1 plus sin square theta, 1 plus sin square theta. This would belong to 1, 2. Okay, let's multiply by 2. 2 times 1 plus sin square theta. This will lie from 2 to 4, and that's the range in which determinant lies. This is from 2 to 4, and this D is the correct answer for this question, as you can see over here. Yes, that's all that you have in this question. And with this, we come to the conclusion of this exercise as well. That's the end of this exercise, that is miscellaneous exercise based on determinants. Chapter number 4 of NCERT Mathematics class 12th. We are ending this chapter over here with this exercise. In the next video, we'll be talking about another chapter. We'll bring you something new again. If you want to get the latest notifications, please subscribe to the channel of Vyas Edification if you haven't done so. And till the next video, all the best.